Hello, Connor. Hello, Spencer. And hello, Jane and Jared. And hello to those who are watching it in the who are watching this meeting in the recordings. I'm always forgetting to bring a tape and put on the crosses here. Okay, not bad. So, physical chemistry. Before we were looking on properties of molecules through wavy nature of electron. Now we believe that there is a wavy nature of ions, like protons and maybe some interatomic distances, just in case we want to check if it may help. For electrons, potentials can be very complicated and different anytime. For internuclear distances, it's always quadratic if it is close to the equilibrium. So it is quite general. No matter what ions are in the molecules, it will be very repeatable pattern. So oscillates in symmetric quadratic potential, moves, oscillates, which means harmonic motion, harmonic oscillator terms. We do want to, if one does spectroscopy, which involves both electronic and nuclear degrees of freedom, the transitions between electronic levels are found different to what they actually are. So if you know for sure from calculations and from other experiments that like you're going from occupied to unoccupied, HOMO to LUMO, and it is literally 2 electron volts. You do experiment and you find it is bigger. Or sometimes it can get smaller, especially if it is emitting. One of the most known and pronounced effect, if we formulate our class as an overview of Nobel Prizes in physics and chemistry, then here there is a Nobel Prize in like early 30s to Raman. I cannot pronounce his first name, something typical Indian. Then comes Raman. Did you hear about it? Did you do Raman experiments or watch someone doing it or watched Spectra? So in other languages, sometimes if people do not like to praise the author, they call it combinational scattering, because like light is scattering on a molecule, and it is absorbed, both absorbed and emit at frequencies which are different from electronic degrees of freedom, because it jumps to electronic transition energy plus a little contribution from quantization of nuclear motion. So it is not my frivolous wish to torture young brains for another chapter. It is real thing. Whew. It's good if you accept. So we do plug in the quadratic potential into time-independent Schrödinger equation with aiming and targeting to do time-dependent stuff later. And now our problem is purely mathematical. How to solve this equation? So kinetic energy is the same, is second derivative over position. And we call it, instead of x, we can call it r, because if it is diatomic molecule, who knows how it is oriented? We care only about distance. So d2 dr squared plus times psi plus r squared times psi equals unknown eigenenergy times psi, right? So if we remove r squared psi, then it will be same as free space or particle in the box. But this stuff where unknown function is not affected by derivative, but multiplied by another known function of the independent variable, sometimes create a challenge. And here is one of the examples. Luckily, this is one of the 5 problems that quantum problems that are solved literally. There are not many, and this one is possible to solve. What is the goal? And I believe there will be slides, but maybe you'll find them more in better chat. So what are the goals? We do want to create a basis set to find eigen energies and eigenfunctions. And if the electron is confined in this potential energy goes up, it means if we have certain energy, it cannot leave. When it tries to leave, the potential will return it. So it will be some functions centered near the equilibrium, right? But on one hand. On another hand, if like if one day world changes so much that all of us will need to teach quantum theory in kindergarten, or you cannot use math. So let's think on this level. What do you remember about eigenstates, eigenfunctions of the particle in the box? How do they look like?
Steps?
Not the energy as function of number of state, not the number of states or density of states. How the actual wave functions, psi, phi, look like. So you're showing something wavy, right? So how does the number of humps of the camel depend on the number of eigenstates?
Transitions back and forth.
So at the end of last section, we were considering time-dependent stuff. And we were looking for exciting from 1 hump to 2 humps. But if you look over all available states, and so if you draw first state, second state, third, fourth, fifth, 10th, how do they look like, and how the number of this nodal points and peaks relate to the number of the state? What you were showing is quite right. You just need to add more.
Each peak is the same.
Very close. I'm with you. Let's just formulate it more precise. Number of peaks and number of states, are they correlated? The larger number of the state, the larger the number of peaks. Yes. Now, and they are all confined in one box. Now, how to interpret it? When we were discussing the plane wave, we agreed that the fringes in this helix, are denser when the momentum is higher and sparser when momentum is smaller. Would you agree that if we go higher up in energy, it would correspond to higher momentum, and therefore the fringes must be denser, right? Okay, so from now on you can teach quantum theory in kindergarten. So it's basically what all this math is for. Now, if the shape of potential is a little bit different, who cares? The overall trends stay the same. So if you go from lower energy to higher energy, it would correspond to quicker motion forward and backward, and it should correspond to a larger number of peaks or more denser fringes. So basically it is what we are going to get. And it should decrease to 0 as we go away to infinity. So it should be something that goes smoothly down, and in the middle it will oscillate. But we need to get a precise mathematical function for such stuff. Okay. What else? Basically, if you open Wikipedia or any textbook and find the solutions and can understand where they come from and how to use them, you do not need this meeting and Monday meeting. A few words about math. You are taking differential equations right now. What is the name of the course?
Intro to differential equations. Intro to differential equations.
And which type of differential equations is declared to be solved in this course?
ODE.
ODE, perfect. You are with him?
I'm not taking differential equations right now.
Okay, so I can guess that in the ODE, D is differential, E is equation. What is O?
Ordinary.
Which means simple, standard. What are not ordinary? How would you imagine based on the course or from your imagination?
Partial differential equations.
Super, super. So the standard, another chapter in differential equations, partial differential equations. Can you tell what it is?
Nope.
That's okay, because you're not taking this course. So typically, one does have only one independent variable. Even if you have many equations, like in a matrix form, it's still one independent variable, either x or time. And when we are speaking about Schrödinger equation, it has two independent variables, time and position, and they're combined together. And therefore, the derivative is symbolized not by straight letter D, but this curvy style, like partial.
Mm-hmm.
And when like 6 in the other side. So the differential equations which combine more than one variables in partial derivatives use slightly different techniques to solve them. And although Schrödinger equation for harmonic oscillator has only one variable, typically it is more related to these partial differential equations. Although it is ordinary, it is eigenvalue problem. Okay. So what else? The mathematical procedure to find eigenstates and eigenvalues, and you already know how they would look for the kindergarten. Right? The higher the energy, the denser the more the fringes. Mathematical procedure includes assumption that solution is a series, polynomial series, like x to the power 0 plus x to the power 1 plus x to the power 2 is some coefficients multiplied by exponential, and then plugging it into equation and finding coefficients, which is quite doable. We can do it in one meeting or in 2 meetings, but I do have a different plan. So I will offer a bypass, which in my words would look as it is simpler, and maybe it is a little simpler. But my actual goal, like if I don't have energy to keep secrets and intrigues, in previous years I was saying, I'll show you short path and you'll avoid solving complicated equations. It's not as much simpler, it's just maybe a little simpler, but on the way we will get new concepts, new abstract theoretical concepts that will be really useful and pleasant and beneficial for whatever we do later. Not only for this harmonic oscillator and nuclear quantized nuclear motion, but for other chapters. Okay, and I'll just keep talking because slides could be boring. So when we were speaking about like the steps and density of states, we got a new friend, a straw man who walks in this space of quantum states. We'll invite this friend to help us once again. So let's assume a space of solutions for this problem that we are solving, for eigenvalue problem, for the time-independent Schrödinger equation, for quadratic potential Schrödinger equation. So let's suppose that we already know energies of each state and shapes of the function for each state. I think you don't mind. So now, if you already have them, let's invite our strawman and offer him to walk up and down along this ladder from lower energy to higher energy state, up and down. Make sense? Now, what, and suppose this strawman is quite silly and does whatever we ask him to do. So we have the lowest state, and typically energy cannot get lower, like if it is only kinetic energy, it cannot get negative. And if it is completely confined near equilibrium, energy cannot be negative. So we can prove it mathematically without solving, but it's kind of evident that there is a lowest energy. Now, let's assume that the strawman is sitting somewhere on the higher steps, higher levels, and we ask him to go one more down, one more down, one more down, and then he's sitting on the lowest level. And we twist his arms and tell, go down. What will happen?
He gets a shovel and starts digging.
What?
He gets a shovel and starts digging.
Okay, well, it's good. But if we have a proof that there is no state below lowest state, and we mandate him to go down, what he just kicks back, tells it's not possible, right? Or he just dies trying to fulfill your order. So how do we formulate this cruel game in mathematical terms? And this, if you are following it, you're doing really great intellectual advance. It's an important thing.
Plugging in equations and finding out they all end up at 0.
Perfect. Yes, absolutely. Were you watching recordings for the next? Then you get a credit for for the thinking. So we will formulate this operation. We always have operators in this course. Operator of strawman going down one rung of ladder down, apply to the lowest state, and this operation should provide 0. So you agree? It makes sense. So if we reformulate the stuff, if we formulate what is a strawman, what is the operator of going down, if you then there is a chance that the equation where something acts on the lowest state gets 0 will be noticeably simpler than actual Schrödinger equation. Okay? Now, if we do have a way to, and by solving we will find the functional shape of the lowest state. So it will be another differential equation, which is, I promise, substantially simple. Now, if you are still playing this game, and we already have the lowest state, now we ask strawman to go one rung up, and by this operation, we automatically will create first excited state. We ask him go one rung up once again. It will be second excited state. So by introducing these jumps of the strawman up and down, and some people call it ladder operators because you climb up and down, one simplifies mathematical task, not so drastically, but simplifies. And in addition, later on, a lot of problems are formulated in a very appetizing way. Appetizing, like if you like math and if you like elegant solutions, not if you hate anything written as equations, then it will not help. But you remember the class material is can be arranged as a three-dimensional space of theories, different systems, and interaction with environment. So these ladder operators will be a really useful concept for introducing interaction with environment later on. So even if you do not have enough time in the class, you will have all fundamentals ready to jump high. Whew. I'm done with free speech, and now I will try to offer maybe some materials in support of this idea. But I think with our mutual understanding of the concepts, it will be quicker and easier. And let me quickly go to the online and check if Connor and Spencer have any questions. Any questions one? Any questions two? Looks like there are no questions. And so sometimes, like on Monday or on Wednesday, you feel it, and in about 2 weeks, you'll set presentations either on Friday or Monday. I think Monday probably would be better so that you can prepare on weekend, but I want to be with the time flexible. It is what we were doing in the lab. And here is the equations that we need to solve. Right? So, second derivative, kinetic energy, R squared, independent function, and here eigenenergy. And you already saw this equation as a last 30 seconds of the last meeting, but the lowest state is what we should get. So we should get only one peak, same as in the particle in the box. Lowest state has one peak, confined somewhere. The energy will be non-zero. And the shape for this peak is expected to be like e to the minus r squared with some coefficients. So basically, we need to find what are those coefficients and what is the normalization constant on one hand. On the other hand, we need to intuitively understand it will be one peak, but we want to get it as a solution from some more rigorous procedure. And I hope very much that this announced stuff on Strawman ladder operator will allow us to get this function within next 24 minutes. So this is what we agreed on. If there are states, and here are very ugly sketches. So there are states, there are some indefinite fringes, and we do have an operation to go up and go down. I need to draw the main curve, the main hero. I'm just trying to show that it wants to go up. So if it goes up, it will be like operator plus. If it will go down, it will be operator without plus. And if we mandate the Strawman to go lower than lowest state, the application of this lowering operator to the lowest state, which we will call phi naught, and energy, if you will A action of phi naught will be equal to 0. And I not only hope, I know for sure positively from composing these slides and from a previous experience that this equation will be simpler than the one, the originally declared one. But in order to do it, we need to formulate what would be the functional form of this lowering operator and how would it be like with differential operator. Now it's time for boring part. So, few more abstract philosophical steps. And you probably noticed that I'm trying to replace math with overall abstract concepts whenever it's possible, like to think more, to solve less, if it is possible. So if we do formulate the energy of the quantum particle in harmonic potential, which means like ions on the spring on a bond, it will be kinetic energy and potential energy. Kinetic is momentum squared, and potential is position squared. Now, one more. I think we are too dense in ideas, but maybe it will save us from some math. Suppose we are we are sitting in one of the eigenstates. Then we are going one step up, one step down. What will be the energy of the system after this operation? No. We can stay in the, let's say, eigenstate number 5. Then we perform operation, go one rung up, one rung down, back to the 6 and back to the 5. What will be the energy?
The initial.
Yes, the initial. So product of this ladder operators going up and going down one after another will keep the energy or wherever it was. So if you do not protest against this idea, then the product of these two operators will be the Hamiltonian very soon, because these two operations do not change energy. And in this idea, our actual total energy operator, which is momentum squared and position squared, must be equivalent to product of these operators. And now I formulate, and I did screw up something with constants here. If I put p here, I shouldn't have minus 8, I shouldn't have a bar squared. Should be, instead of this, it should be plus. So how can we, what should be the functional form of this A diagram A in order so that by multiplying them by each other, we will get this Hamiltonian. So if you assume this ladder operators are composed only on position and momentum, and you take square here, what should be the power of position and momentum in the definition of ladder operator? 2. No. After taking square, after taking this 4. No.
Oh, geez, no.
We have unknown operator A. By taking square of this operator, we are getting second power of momentum and position. Mm-hmm. What is the original power of momentum and position in the operator A?
1.
Yes. 1. So if we define them as linear combination of position and momentum, maybe with some unknown coefficients, then by multiplying these two things, doing some algebra and canceling some terms, we have a hope to arrive to the total energy operator in the standard form. So before we will practice this glorious way of mandating state lower than ground state and getting 0, we need to define what is A. And through this consideration, we see that it will be just linear combination of position and momentum with unknown coefficients. And it is my task to find what are those coefficients. Basically, if I will accept that Hamiltonian has this form or this form, I just plug in this stuff into here and do some algebraic manipulations until I solve for this unknown coefficient, right? It's quite boring. I'll try to jump through it as quick as possible because we need only the result. This exercise is not needed and even would be useless as a homework. So linear combination, unknown number, unknown coefficient here and there, unknown coefficient here and there, multiplying together should give us regular stuff. And I do want to find this coefficient, which I will call P and M for plus and minus. Okay, and if I carefully practice this stuff, I just did it once and then repeat it a couple of times, but we need, again, this is, I wouldn't say garbage, but it is not the main focus of what we are doing. So composing products of this, we should get P1, M1 should give the factor in front of kinetic energy, P2, M2 should get a factor in front of potential energy, and the cross terms should be zeros. So we have several equations, and if we solve for them, if you find some coefficients are symmetrically equal to each other, we will get that P2 is square root of mass or 2 times frequency, and P1 will be Planck constant over square root of 2 masses. So doing this from scratch, I don't know, maybe for you it will take quicker. For me, what will it took like more than an hour to figure it out. And typically, it is skipped in textbooks. It is just defined. Those coefficients are defined. But if you do plug these coefficients into here, and we set that those are complex conjugates, then we get a definition of this operators. Yes. So we do plug in solution of this equation, and then we get a definition. So that with this P1, P2, and 1 into coefficient. So the operator A without dagger, which will be the one that brings us lower down. So position plus momentum, and here are these coefficients.